All right, so we're in section 2.2 now, and this section is called the limit definition of the derivative. All throughout section 2.1, our focus was on instantaneous rates of change. We also talked about average rates of change, but the primary reason we talked about that was to lead into the discussion on instantaneous rates of change. We talked about how to find an instantaneous rate of change, which we could also interpret as the slope of a tangent line to a function at a particular number, at a value x equals a. We did some examples of those types of problems. As we saw in that section when we worked through those examples, finding that instantaneous rate of change using that limit of that difference quotient, the way that we defined it, it's kind of a lengthy process. There's a lot of steps, and it just has a tendency to take some time and effort to solve one problem. While it's not, the worst thing ever, it's not terribly efficient, especially when you consider the fact that for a particular function, you may want to evaluate the instantaneous rate of change in that function for various different numbers. You may not just want to do it for one particular value. I give an example here. Say there's a company that wants to know the instantaneous rate of change in its profit function. Remember, we talked about profit functions in the previous section. For x equals these different values, 10,000, 20,000, 30,000, so on and so forth, all the way to 60,000. That would require walking through that limit process 6 separate times, which is really not very efficient. So what we want to do in this section is develop a technique for doing what we did in section 2.1, but more efficiently. So here's that limit definition that we've already been using. If you want to find the instantaneous rate of change in a function f at the value x equals a, then you evaluate this limit, the limit of this difference quotient right here. But if we want to be able to do this for various different numbers a, not just a single number, but for the same function f, then one thing we could do to make that a little bit more efficient is replace that a with an x. In other words, we think of x as a variable. So what happens is when you evaluate this limit where that a has been replaced by an x, once you've evaluated everything, you're going to be left with a function of x. You could then plug any number that you want into that function, provided it's part of the domain of that function. And what would come out is that instantaneous rate of change in f for whatever you plugged in. So you're basically creating a function that gives you instantaneous rates of change as an output, or gives you slopes of tangent lines, if we want to think of it from that perspective, as an output. That function is what we call a derivative. So here's our kind of formal definition. If f is a function, then the derivative of f, which we use this notation for, f with that apostrophe, we read that as f prime. Then the derivative, which we denote by f prime, is the function whose domain consists of those values of x such that the following limit exists. It's this, f prime of x is equal to the limit as h approaches 0 of this difference quotient. And notice now the a is replaced by an x. So let's walk through an example to see what this really looks like in practice. We have a function here, f of x equals x squared minus 5x. And what we want to do is find f prime of x, the derivative of f. And then once we've done that, we're going to use it for something. We want to use that derivative to find the slope of the tangent line to f at x equals 3. So to start, I have to set up that limit. So I'm actually going to do this. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So as I evaluate this limit, let's look at the function. X plus h is being substituted in for the x right here. So that's going to look like this. The limit as h approaches 0 of x plus h quantities squared minus 5 times x plus h minus f of x. But this is f of x right here. So as before, we put that in parentheses to make sure that minus sign is distributing to all of those terms. Okay, now I'm going to expand things out as much as I can. So this process should feel very much the same as what we did in the previous section. The only difference being that I have this x floating around in here instead of a constant. I'd get x squared plus 2xh plus h squared. Distribute that negative 5 in, so minus 5x minus 5h. Distribute the minus in here, so you get minus x squared plus 5x all over h. As we saw in section 2.1, this process involves kind of expanding things out as much as possible in the numerator, in the case where we have like a polynomial like this, and then trying to get things to cancel out. Lots of stuff cancels out. I have x squared and negative x squared. Those cancel. Negative 5x and positive 5x. Those cancel. Now if we look at what's left, I only have 3 terms. 1, 2, 3. All of those terms contain an h, at least one h in them. So I have the limit as h approaches 0 of 2xh plus h squared minus 5h all over h. Cancel this h with one h from each term. So now I've got the limit as h approaches 0 of 2x, I'm off screen there, 2x plus h minus 5. At this stage, I can use direct substitution, and the only place an h is even showing up is this middle term here. So when I plug a 0 in, it just leaves me with this, 2x minus 5. Okay? Now, unlike section 2.1, I didn't end up with just a number. I ended up with a function of x, and that's where things are different in this section. But going up here, it says use this derivative to find the slope of the tangent line to f at x equals 3. Well, remember, the slope of the tangent line is what we get from this limit of this difference quotient. It's one of the interpretations of it. But I don't have to redo all of this by putting a 3 in here. The 3 would just take the place of that x. But now I have a function of x that came from that limit of that difference quotient. So all I have to do is plug that 3 directly into here, and I get that slope. So I can write that this way. F prime of 3, remember that's how we denote this function, but I'm plugging a 3 in, which equals 2 times 3 minus 5. That's equal to 1. And if you notice how quick that went. So obviously it took some work to get to this point, but once we had this function, I was able to find the slope of that tangent line just by plugging the number directly into that function and doing one quick step to work it out. And notice that because I have this function, if I then wanted to go on and find the slope of the tangent line at x equals 4, 5, 6, 7, 8, 9, and 10, so all of those additional values, I wouldn't have to do all of this again. I would just have to plug those new numbers directly into this function, which is very quick to do. So that's the benefit of thinking of the derivative as a function the way that we are here. Okay? Now, right here, I have a graph of the function from that previous example. So again, here's that function, x squared minus 5x. That would be, because it's a quadratic function, we would get a parabola from that. It's that red parabola. And then notice my derivative, 2x minus 5, that's a linear function. So the graph of that derivative is a line. It's a little bit small on the page here, but the red graph is f of x. That's what this says. The blue line is f prime of x. That's what it says right here. I wanted to graph these both on the same set of coordinate axes because we can do some comparisons between the two to see how they're related to each other. In particular, I want to pay attention to slopes of tangent lines on this red graph and sort of correlate them to the values, the y values in particular, of different points on this blue line right here. So notice, first of all, it's a little bit hard to see, but right here, where the vertex of that parabola is, that's going to correspond to x equals 2.5. That's what the x coordinate of that point is right there, okay? And so You can find that easily enough because if you notice, that's where this blue line also crosses the x-axis. So you can go to your derivative, 2x minus 5, set that equal to 0, and then solve it, and that's how we would have gotten this. But notice that for all of the x values to the left of 2.5, the blue line is giving me negative y values. It's below the x-axis. So f prime of x is negative whenever x is less than 2.5. But what does that mean in the context of the original function? Well, remember, if we have a negative instantaneous rate of change, or we can interpret that as a negative slope for our tangent line, then our tangent lines are all going downhill. And the implication of that is that the original function f of x had to have been decreasing. So we can associate negative derivatives, which we see by the derivative function being below the x-axis. That would we would interpret that as a decreasing function for our original function f. Notice if we use x values that are greater than 2.5, the derivative, that blue line, is above the x-axis. So the derivative is positive for all of those x values greater than 2.5. What can we say about the graph of my parabola? So as I go from 2.5 and increase in my x direction, that function is increasing as opposed to decreasing like it is over here. That happens because all of the tangent lines to the graph have positive slopes, which is what's indicated by this positive derivative right here. Okay, so we have this direct relationship between whether our derivative is positive or negative and whether the original function is decreasing or increasing. There's one more thing worth pointing out. When x is exactly equal to 2.5, our derivative is equal to 0. That's what it means when it crosses the x-axis. But what can we say about the slope of the tangent line of f of x, this parabola, at 2.5? Well, that tangent line would look like this. Its slope is neither positive nor negative. Its slope is 0. So I can say that f prime of 2.5, remember that's the slope of f at that point, is equal to 0. And we get a horizontal tangent there. So that's also really, really important to notice. Anywhere where the derivative of our function is equal to 0, our graph is going to have this horizontal tangent line. Okay? So that's kind of what's being described right here. Let's do an example where we have to use that information. This example says, determine the value of x for which the graph of 2x squared minus x plus 6 has a horizontal tangent. Now, there are ways to do this without calculus. If you remember, the graphs of quadratic equations from algebra, you know that those graphs are parabolas like what we have here. And just from what the graph looks like, it makes sense that that horizontal tangent would occur at the vertex of that parabola. So if you know some techniques for finding the vertex of a parabola, given its equation, then that's great. But we're going to try approaching this using calculus instead. One thing that's actually missing here, I should have something that says like f of x equals. That was left off for some reason, so just put that in there. So we said up above that this graph will have a horizontal tangent line wherever its derivative is equal to 0. So if I want to answer this question, I need to first find that derivative. So f prime of x, let's work that out. It equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? For this particular function, what does that look like? So plugging x plus h in for all of the x's, I'm going to have this. Limit as h approaches 0 of 2 x plus h squared minus x plus h plus 6 minus f of x. So again, put that in parentheses. 2x squared minus x plus 6. And that whole thing goes over h. Okay? By now, you've probably done this process enough times that you're probably getting somewhat quicker at it. So if I expand that x plus h squared out and then multiply everything by 2, I'll get 2x squared plus 4xh plus 2h squared. Distribute the minus in there. minus x minus h plus 6, that's that guy. Distribute this minus sign in, minus 2x squared minus, that's a plus actually, plus x minus 6. That whole thing is over h. And at this point, we cancel as many things out as possible. 2x squared and negative 2x squared. Plus 6 minus 6. What else do we have? I have a minus x and a plus x. All of that stuff cancels out, and it looks like I only have 1, 2, 3 terms remaining, all of which have one of those h's left over. So I have the limit as h approaches 0 of 4xh from here plus 2h squared from there minus h right there all over h. Cancel an h from each term, so that goes away. I lose one of those h's. I lose that one, but remember it leaves a 1 behind, so that's really a minus 1, and that all canceled. Limit as h approaches 0 of 4x plus, there's still an h there, so 2h minus 1. The direct substitution step works now, so I could plug a 0 in for h, and I have 4x minus 1. Okay? Quick side note before we try and answer this question. This process still is lengthy, right? Even though it's more efficient because we can use it for multiple slopes of tangent lines or multiple instantaneous rates of change for the same function, it still takes a lot of work to get from here to here. So just a quick preview, in the next section, 2.3, we're going to talk about some techniques for finding derivatives of particular functions where we don't have to do any of this. We're going to talk about some special rules of taking derivatives of different types of functions, polynomials, exponential functions, radical functions, all those different things, where this process, instead of taking all of this work, takes about 5 seconds. So we have to do the hard stuff first before we get to use the shortcuts. All right, now at this point, we haven't answered the question. It says we want to find the value of x for which this function has a horizontal tangent. So, hold on one second. Okay, so remember, a tangent line is horizontal if the slope of that line is equal to 0. So I can take my derivative, 4x minus 1, and just set it equal to 0, and then solve for x. That's a quick one to solve. It's a linear equation. X would equal 1/4. You can see what the steps are there, I hope. Okay, so that one was pretty straightforward once we had that derivative. And that's the idea. The derivative function is really, really useful for answering a whole variety of the different questions like this. Let's try another example where we're doing a derivative of something that's not a polynomial. In this case, we're just finding the derivative. We're not finding the slope or finding where the function has a horizontal tangent or any of those sorts of things. So I want to find f prime of x, which is equal to the limit as h approaches 0 of, again, f of x plus h minus f of x all over h. Now you can look at this and you can think, do you really need to rewrite the definition every single time, or can I just jump to the next step? And technically you can. I like to do this because it helps ingrain it in my memory, so I remember exactly what's going on. So what does this look like? Limit as h approaches 0. X plus h is substituted in for the x right here, so I'm going to get the square root of x plus h plus 4 minus, and then in parentheses over here, f of x. So that's the square root of x plus 4 all over h. Okay. We have to work at simplifying this now. So notice if I were to distribute this minus sign, this plus 4 in here is going to become a minus 4, which would then cancel with the plus 4 right there. So that's going to leave me with this, square root of x plus h minus square root of x all over h. And this is one of those difference quotients involving radicals that we have talked about how to solve. We use a different technique for these than we did for the previous examples. We multiply by a conjugate. So square root of x plus h minus the square root of x, its conjugate would look the same, but with the minus swapped out for a plus. And we get this. Okay, now looking at what would happen next, remember, when I multiply this numerator out, I'm going to get this thing squared minus that thing squared. But squaring it just gets rid of the radical. So I have x plus h minus x. That's now in my numerator. Down in my denominator, I have h times this expression, but I'm not actually going to multiply the h out. I want to leave it in this form. X plus h plus square root of x. Okay, the reason I wanted to do that is because these x's are going to cancel now. X and negative x, those cancel. And then because I just have an h here, it'll cancel with the h in the denominator. That'll divide out. So that becomes a 1. That just goes away. And now I have this, the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now at this step I can actually use direct substitution. And the reason why is because I have a plus here instead of a minus. So when I use direct substitution, this is going to become the square root of x, and I'm adding another square root of x. So I don't get a 0 in my denominator anymore. I get 1 over the square root of x plus the square root of x, or put a little bit simpler, 1 over 2 root x. That is the derivative that I'm looking for. Okay, so like we said, in this example, we're not going to do anything in particular with that derivative. We're just finding it. We wanted to get another example under our belt. Okay, all right. A little bit of notation to talk about. So when we're doing derivatives, we've talked about how if you have a function f of x, you can write f prime of x to denote its derivative. As you know, a lot of the time we don't always call a function f of x or something like that. Sometimes we just call it y. So like y equals x squared. In that case, you can use that prime notation there as well, y prime. This is sometimes called Lagrange notation. It's named after a mathematician from a very long time ago. And we're going to use this notation a lot. Another type of notation that's used very frequently is what's called Leibniz or Leibniz notation. I always can't remember which pronunciation is correct. And this notation looks like this, df over dx. Or if we're thinking of our function as y equals some function of x, it's dy over dx. We actually don't say the over, we say df dx or dy dx. That's the pronunciation of that. There's a version of Leibniz notation that we use here as well, d dx. So if there's no additional letter here, if it's just d dx, then this is basically what we call an operator. And what it does is, by itself, it doesn't mean anything. But if I put a function next to it, it's saying take the derivative of that function. Okay? The x that's showing up in the denominator, its role is to tell me what the independent variable of that function is. And a lot of the time we say take the derivative with respect to x. So that's like telling the reader what the independent variable of that function is. Whereas the thing showing up in the numerator is the label for the function itself, f or y or whatever. So like this is saying, kind of mentioning what I mentioned previously, we pronounce this as df dx, dy dx, or d dx, okay? So let's get one more example in before we end this first part. I have a function y equals 4 over x plus 3, and I want dy dx. So dy dx is just an alternative definition for the derivative, okay? So I think this time I'm not going to use the f of x plus h minus f of x notation because I didn't call this function f, but I can still do the same basic idea. So I have my first term, which is this function, but with an x plus h plugged in for the x, minus this function by itself with just x in there, all over h. We've dealt with these types of functions before as well. We want to clear out these smaller denominators. So I'm going to multiply my numerator by x plus h plus 3 times x plus 3. I'm just grabbing both of these smaller denominators, multiplying them together, and then putting the same expression in my denominator so that this expression is equivalent to 1. Okay, the purpose behind doing that, limit as h goes to 0, is that when I multiply this through, this term, or this denominator, will cancel with that, leaving me with 4 times x plus 3. And then when I distribute this to that rational expression, the x plus 3's will cancel, and it leaves me with minus 4 times x plus h plus 3. In my denominator, I don't distribute anything out. I'm just going to leave this the way that it was written. X plus h plus 3 times x plus 3. Okay? At this point, distribute the 4 and the negative 4 in. So we have limit as h goes to 0 of 4x plus 3 minus 4x minus 4h. Negative 4 times 3 would be minus 12. And then this denominator is the same as before. We haven't done anything to it. Okay? And just as you keep seeing over and over again with these problems, cancel things as much as possible. So 4x, negative 4x, those are going to cancel. 3, oh, did I miss something there? Oh, no, we're fine. So here we're going to have, oh, I feel like something important is missing. What's missing here? Oh, I know what it is. I made a mistake here. 4 times 3 is 12. I just wrote plus 3. Okay, things were not working out the way they should have. That's the reason why. So I should be getting this 12 and this negative 12 canceling. That's what happened. So what's left up here is negative 4 times h. And because that's the only thing left, the h there will cancel with that h right there. Now we're good. The limit as h goes to 0 of, what's left now is a negative 4 over x plus h plus 3 times x plus 3. It's now safe to use direct substitution to evaluate this limit because when I plug a 0 in, I just get x plus 3 times x plus 3. Which is the same thing as this, negative 4 over x plus 3 squared. There's my derivative. Okay? All right, that's going to be our last example for this video. We'll wrap things up in the second video.